And thank you to LambdaConf for the opportunity to be here. So I am an open source contributor. I actually contribute to a little project you may have heard of called Scalaz. And in particular, I'm working on version 8 of the software library. It's been years since we released a new major version, and it's about time. We've learned a lot about functional programming in Scala in the meantime, and it's about time we had a new release of that software version. So today I want to talk to you about Scalaz 8, and in particular how you can use Scalaz 8 to solve some of the problems that people use actors for. Before we get started, however, a little disclaimer. LambdaConf made me put this up there. Are there any actors in the audience? I'm sorry, this may not be a safe space for you. In all seriousness, though, I may poke a little fun at actors today, but the reality is if you use any tool out there, whether it's actors or PHP or heaven forbid Go, if you use any tool out there to deliver business value, I have enormous respect for you, okay? And that's, at the end of the day, that's what matters, is delivering business value to your users. Uh-oh, where's my emoji? There should be an emoji there. So, what is the ultimate question of software development? I know what you're thinking. It's probably, how do we build really large, complex software systems out of little tiny pieces that we can reason about locally and type and understand and assemble together to solve complex problems? I'm going to go out on a limb here and say that's probably not true, that the ultimate question of software development probably has something to do with bending light and maybe being reactive. Now, how do I know this? Well, I know it because I know what the answer is to the ultimate question of software development. And it's this thing called an actor. And an actor is, in essence, a partial function from any to unit. You feed it something, and it'll do something, and it might blow up while it does it. So surprisingly, there are some use cases at which actors absolutely kill it. And what I want to do today is go through each use case and show you how actors do it, but also give you a feel for how I might solve that problem if I were using Scalaz 8 to solve it. And then one by one, we'll look at each one of these use cases and we'll try to answer the question, are actors really the best possible solution for this use case? So these are parallelism, concurrent state, persistence, and distributed computation. So let's take a look at the first one, parallelism. So over on the left-hand side, you have an example of using an actor pool to do a bunch of work in parallel. We have some heavy-duty CPU-intensive encryption to get through, and so we want to do a bunch of this stuff in parallel. So we create the actor pool, we create a router, and then we can start processing these chunks in parallel. And then over on the right-hand side, you have the Scalaz way of doing that, which is just to run all this stuff in parallel. And I'll admit there's a certain beauty, I guess, to the object-oriented way of solving this problem using actors. But on the other hand, the Scalaz 8 solution is one line of code and is likely to be many times faster than the Akka solution. So probably, maybe parallelism turns out not to be a killer use case for actors. Well, there's still hope. How about concurrent state, right? Actors are really good at concurrent state. So let's take a look at a problem involving concurrent state. This is a counter actor, one of the simplest examples that you'll find all over the web, and it is responsible for updating a counter. So you send it a message, and lots of different threads can send it a message, and it will atomically update this counter because the work done by the actor in the local state will be processed on a single thread. And this is all well and good though, but in Scalaz 8, we have this wonderful thing called IOREF. And IOREF has this atomic function called modify that can perform things atomically without using an extra thread. So the right-hand side actually implements essentially the same functionality as on the left-hand side, only it's probably going to be anywhere from 10 to 100 times faster. And of course, there's way less code, and you can actually have types associated with it. And that scales, by the way. So you can do this with all kinds of data structures. Any immutable data structure that you can imagine, you can use this same approach for. And it's going to be most likely really, really fast, except in cases of tons and tons of contention. And we'll talk about that in a bit. So I don't know, I'm not so sure that concurrent state is necessarily the killer application for actors. Maybe persistence, Akka persistence, right? Well, over on the left-hand side, you have an example of using persistence to do pre-persistence of messages before they're processed by an actor. But again, like, this functionality isn't game-changing or anything. All we have to do is call a persist function on our payload before we process it. And as long as we have ACID guarantees about that, it's kind of the same thing. So probably not. Persistence is probably not the killer application for actors either. Well, what about distributed computation? So Akka actors can be used in a distributed cluster, and you have things like sharding, and you have singleton actors, you have actor groups, so you can take and partition a cluster of actors into different groups that have totally different responsibilities. And that's kind of cool. And honestly, Scala Z8 doesn't have anything like that. So maybe distributed computation is in fact the killer application for Akka actors. I know what you're thinking. Probably we're working on our own version of distributed computation for Scala Z8, but no, I don't really have any plans to do anything quite like distributed clustering in Akka. For example, losing messages over the wire, or the auto-danning feature that should never ever be used under any circumstances, and so forth. This is maybe not how I would design a distributed compute solution if I were designing it. So I'm going to give this one to Akka. Akka actors for the win. If you've got a problem in distributed computation, Akka actors, they're a reliable, solid choice. But if we go back and look at all these different use cases, we have to be honest with ourselves. We have to ask the question, is a partial function from any to unit the answer to the ultimate question of software development? Can we do better? That's the question. And so what me and a bunch of other Scala Z8 contributors did is we got together in one of our top secret confidential war rooms, and we brainstormed on how we could do a better job than Akka actors. If we were coming up with a next generation purely functional actor design, something that could just sort of blow away the problems with Akka actors, what would it look like? And then we had an epiphany. A function from A to B is a next generation purely functional actor. And it has input messages that are typed A and output messages that are typed B. Wow, look at that. I know what you're thinking. You're thinking, John, you're just trolling. And you're kind of right, because where's the monad, right? We need a monad in there. There. Now we're talking. Now we have this input message, and generating the output message can require some sort of effect. This is an effectful actor. And actually, if we want to generalize this even more, and of course we do, I'm a Scala Z8 contributor after all, then we wrap that in another effect type, so we say the mere act of creating an actor may require some effect, which might be different than the effect required to produce an output message. And There you have it, a next generation purely functional actor design. Let's take a look at this counter example and see if we can implement it using Scala Z8 primitives, using the paradigm that I just introduced. So here's our first stab at this. It's an increment function. We pass it the number of things to increment the counter by, and in theory it's going to do that and then return us the new value of the counter. So here's the first stab at that, and you should notice that this has a serious problem. Inside this function, we create the counter, and then we modify it and return the value. So the next time you call this function, the counter will be recreated. So you're never going to count anything. So this is not exactly what we want. In order to get what we want, we have to use the most powerful formulation that I introduced on the last slide. So here we have this make actor effect. And once we call it, it's going to make an actor in the I/O monad. The actor itself will be nothing more than a function from some input type to output type, in this example int. And then the implementation of this becomes quite trivial. We create the counter, and then we create the actor as just an ordinary function that modifies the counter. And then we return, in that effectful I/O action, we return the actor. And of course, this isn't a real actor, is it? Right? Because for one, it has all these crazy types, and two, we can't use the bang symbol. So if we don't have the bang symbol, it's not an actor, it's not very useful, so let's go ahead and add that. So now we have a type of things that are actors, which of course are just effectful functions, and we can recast our make actor to actually return us something that is an actor inside the I/O monad. And then we can add this cool little actor syntax, a synonym for application, in case you prefer the bang symbol to function application. And there you have it, an example at the bottom of this actor being used. We're sending it a message, we're saying increment this counter by 20, and it's going to return the new value. Now this is totally thread safe. It can be called from any number of threads, and it's going to be incredibly fast compared to a real actor. Almost no overhead. Also, it's completely typed. Both the input message of this actor and the output message are strongly typed. So you know what this does. There's no black box here. There's no dynamic typing at all. It's just an ordinary function. And this approach, as simple as it is, works amazingly well for any type of concurrent state problem in which there's relatively low contention. For extremely high contention, the more queue-based system that Akka actors use ends up being more performant. But we can still do that, actually. All we have to do is use something called an asynchronous queue that will be shipping with Scala Z8. And in an async queue, the formulation of this actor becomes only slightly more complex. The guts of it are as follows. We create the counter effectively. We create the queue. The queue is nothing more than a queue of tuples of input messages and promises for the output messages. So you could generalize this if you wanted and stick it in a function so you'd never have to make it again. And then the worker, we just take something from the queue, we flat map that to an action that modifies the counter, incrementing it by the first element of the tuple. And then we flat map that, modify will return the new value of the counter. So we flat map that to the completion of the promise. So we complete the promise with the value at which the counter is set to. And then we call dot forever, which is a function on I/O that will repeat that forever. And then we fork that off into a different thread. So one line of code to do all that. And all the values here are totally immutable. So we're not actually doing anything crazy. And then finally, we create an actor which creates the promise, sticks the promise and the number to increment it by into that queue, and gets the future or the I/O action associated with that promise. So here we have it. This is basically Akka actor in a few lines of code. And this async queue will perform better than the I/O ref in cases of extremely high contention. If you have tons of threads hitting something at once, then this is going to perform better. All right, well, technical difficulties. Oh, okay. So one of the really cool things about actors being functions is that functions compose. We can have function combinators. For example, we can have a combinator that persists input message to an actor. We can have a combinator that persists output messages. We can actually combine those to get another combinator that persists input and output messages. So because these things are not opaque black boxes with no types, rather they're totally transparent, well-typed functions, we can compose them together in all the ways that you compose ordinary functions. And in fact, you can actually take two actors here and in a type-safe way, compose them together to get another actor. So this is stuff that's not possible with Akka actors because they aren't ordinary functions, well-typed functions. Of course, just because we can emulate actors with Scalaz at 8 doesn't mean necessarily that we should. I think oftentimes in software development, we look for a magic bullet, something that can be used in all situations regardless of how good it is. And the reality is that other than, well, really functions and data types, there is no magic bullet. Like different use cases require we make different trade-offs. And using some designs, by constraining those designs, we gain a tremendous amount of liberty to provide strong guarantees on implementing those constraints. And that goes doubly true, I think, for distributed systems, where even a tiny little, if you're able to give away some guarantee in a distributed system, you can gain tremendous benefit in whether it's consistency or failover or something like that. So I would encourage you to not limit yourself. Don't reach for an actor just because it's the thing that everyone else is doing. Instead, think in terms of building blocks. And Scalaz at 8 provides you the building blocks you need to compose well-typed, purely functional, highly performant applications from small, simple pieces that you can reason about in a local way. An example of 4 of the building blocks that I've used in these examples include the ability to do parallelism, so trivial resource-safe parallelism, the ability to do intra-thread synchronization, the ability to do signaling, that is sort of awake a bunch of things that are awaiting on some value, which you do with promise, and then the ability to create asynchronous actions that are going to resume at some point in the future. So these are orthogonal, composable building blocks that you can snap together to solve problems. And in many cases, the solutions are way simpler than the Akka equivalents, and they're type safe, and they're also a whole lot faster. Okay, so a little bit of trash talking here. So Scalaz at 8, the effect system in there is up to 200 times faster than the future that ships with Akka. That is really, really fast. So if you think the reason for using Akka's future is performance, think again. Purely functional code can actually be a whole lot faster. Also, the effect system in Scalaz at 8 is totally type safe. There are no partial functions, and everything is well typed. There are no any's, and everything is as polymorphic as possible, which gives you a lot of flexibility and the ability to understand your code by looking at a type. Because everything is purely functional. So every function in the Scalaz at 8 effect system is total. It is deterministic, and it has no side effects. which gives you an unprecedented ability to reason about your software merely by looking at type signatures. If you saw a function any to unit in Scalaz at 8, you would know exactly what that function did. It would return unit, because that's the only purely functional thing you can do. And that ability to look at a type signature and to know for a fact what a function can or cannot do is amazingly. It liberates you to program without fear, and to program without having to drill into every single function that is called by the function you're looking at and exhaustively explore the entire thing and simulate the program inside your brain in order to understand what's going on. You don't have to do that anymore. Every function has an input and an output, and they're all total, they're all deterministic, none of them have any side effects. Scalaz 8 has very powerful combinators for producing resource-safe programs. So if they open resources, you have guarantees that those resources will be released. If you spawn threads and you supervise them and your thread shuts down, you have guarantees the other ones will be shut down. So these strong guarantees give you the ability to write leak-free, enterprise-grade software that gets stuff done, and you spend less time tracking down exhausted file handles in some Linux server, and more time writing, contributing features that add business value to your software application. And then Scalaz 8 effect system is extremely compositional, being just sort of very generic functions and types that are governed by type classes like functor and applicative and monad and so forth. Everything fits together, and it fits together very nicely, and it allows you to build bigger things from smaller things in a way that's very, very reasonable, that you can reason about locally. And then Akka futures and actors, well, you know, it's kind of the flip side. It's a lot slower, type unsafe, and type actors sort of get you part of the way to a function, but like, why bother? Why not just start with a function? It's not functional, or as I like to call sometimes, dysfunctional. It's resource unsafe, so there's no way to provide guarantees about resource unallocation. You have to do that in a number of different ways. And it doesn't really compose. Stuff doesn't really fit together. Black boxes that receive anything and don't return anything, they don't fit together well. And you see that a lot in large Akka code bases. It's really hard to reason about code bases that overuse actors to do lots of single machine processing. That said, there are a few reasons to choose actors. First off, your code is way too fast. Well, insert a bunch of actors in there and that problem will be taken care of. Maybe your users don't think your application's doing anything useful because it's too fast, so just throw some actors in there. Your code is too composable, so sometimes too many pieces fit together, and like it's too easy to solve problems from basic building blocks. And then what have you got to do? Like that's not fun, snapping together building blocks. Ad hoc solutions, that's where it's at, so throw some actors in there and stuff will stop composing. And then finally, when your code's too easy to understand, well, there's nothing that will solve that problem more than a partial function from any to unit. Job security, that's where it's at. And in seriousness, actors are sometimes useful. Even assembly language is sometimes useful, but we can often do better. And I think hopefully you've seen a few examples where, yes, we did better. So that concludes my presentation. I would love to give folks a tour of the Scalaz 8 effect system. So I'm available for office hours here in a few minutes at 1 o'clock. If you want to sign up, I'll be happy to give you a tour. And I want to thank Scala for having me at this conference, and thanks to all you wonderful attendees for showing up to my crazy talk to hear me bash Akka actors. Thank you very much. Hope to see you again next year.
Thank you, John.